Oh, welcome, Dankrad. So I guess your introduction's kind of mostly made, but I had some sort of introductory observations. So, Ethereum researcher, we know that. Recovering physicist. We want to cover a little bit about your academic background.
Getting better. Getting better, yeah.
Getting better. Getting well. Prefix of Ethereum's data sharding. Freelance reality policeman on Twitter, and I kind of want to cover that as well. And a sub 3-hour marathon runner, and that's kind of, I guess, in decreasing orders of relevance. But so I guess sort of first question is, how did you get here? We heard just now that you had an academic background in physics, undergraduate, postgraduate, PhD. Why not continue with the research? And what were you doing in the intervening years between that and Ethereum, and what led you to Ethereum?
I did my PhD in physics at the other place, obviously, a few years ago. At the end of that, I kind of knew that an academic career was not the right thing for me. I enjoyed research, but I didn't enjoy academia that much. I started working at a tech consulting company and had a few more stations in tech until founding my eHealth startup. And I think like round about 2018 was the time when I started getting a bit bored with that. I still had my startup, but I didn't, I guess like with my physics background, I didn't feel that challenged anymore by tech, just pure tech. And around that time, I was also approached by Justin Drake, who I'd worked with before, and he suggested, why don't I do something in Ethereum research? So I started working on some problems in 2018 and found it just very exciting. Like, yes, crypto problems, as in both like blockchain and cryptography, are often like very interesting and from the math side, and often like let you apply many different domains at the same time, in a very similar way that studying physics does. So I found it very interesting, and about half a year later, I joined the Ethereum Foundation to do this full time.
Thank you. And as far as the background that you had in the physics, any carryover except sort of basic sort of, I guess, advanced numeracy, but was there any sort of carryover between the kinds of research problems you were studying as a physicist? Actually, what kind of physics are we talking about? What were you doing? Was there anything there or at Palantir or anywhere else that gave you any advantaged background in cryptography?
I would say almost no. Like it was, I did high energy physics, so it was all sort of partial differential equations, stuff like that, all continuous math. So unfortunately, none of that actually applies to cryptography. But the good thing is a lot of it is thinking basically in the right categories and being able to actually do math. And in that terms, like, I guess I would say like whatever you do in mathematics or physics or any adjacent field can be an excellent preparation.
So you turn up at the Ethereum Foundation 2018-19, that kind of time, and at that point the sort of the migration of Ethereum, it's not kind of formalized with that famous post of Vitalik, but it's clear where the direction of travel is heading. We had Ellie, who we just heard from, and a few other companies working on Zk rollups. Could you give us a quick account of the various attempts to scale Ethereum, I guess the various sort of research panics that the Ethereum network had kind of been through intellectually, and the various, why did some of those attempts to scale, I think it was more, at least as much on the execution side as the data side, possibly why did they fail, and or was it just the roll-up world was obviously coming, and that's where data began to be the focus? But can you give us a quick potted history, how you saw it when you came in?
I mean, so Ethereum scaling, or generally scaling, is a huge topic, and I probably can't possibly touch up on all of these. Actually, so in 2018, execution sharding was still very much alive and was the Ethereum roadmap. So that shift happened more in 2019, 2020.
Can we just make clear, what execution sharding, what is that and how is that different to data scaling?
Yeah, so one of the building blocks is the same. So like blockchain scaling, like if you look at the blockchain stack, there are different things that you need to look at. There's consensus, there's data, and there's execution. And consensus basically has nothing to do with scaling, because consensus, like how many validators you have or anything, has nothing to do with how many transactions your blockchain can process. What you need to scale is how you can actually put all these transactions on the chain, and how you can do the state updates for these transactions. Execution sharding was the first attempt to do this, which was saying, okay, like instead of having one big blockchain, we create many parallel chains basically that are coupled in some way, so they share the consensus, but they are decoupled in their execution. And then we have a different construction that's called data availability sampling in order to like make sure that all this data is available. And this was on the roadmap of Ethereum pretty much since the beginning. So it's part of the Ethereum white paper that this is going to come at some point. This was very much still alive when I joined the Ethereum Foundation. And then over the year of 2019 came the realization that, well, what happened basically is that inside the Ethereum Foundation, actually, by a team led by Barry Whitehead, they built something called the ZK rollup. So they built this first thing where they said, hey, what if we just do this thing where we put transactions on the chain and we create a zero-knowledge proof that they're correct. Actually, a validity proof to be precise, because it doesn't use the ZK property of the proofs at all. And so from then on, people started realizing, well, actually, if we had a base chain with lots of data, then we could actually already do everything we want using this construction, so by basically adding rollups to it. And then over the year, basically at some point, people were like, well, let's just forget about this execution sharding thing, because like this is good enough, this is going to be much simpler, and it became the main Ethereum goal to just as soon as possible build out this data layer.
So this kind of roll-up view of the world, where you have these separate networks that are all kind of, from a consensus perspective, sort of subservient to L1, so they tap into L1 for this is the record of economic events. Is that a kind of what you call execution sharding? Like how close does that really get you to the sort of the full execution sharding? Because it sounds very similar. You've got all of these little computers running all over the place. How similar is it, and how far away is it from the execution sharding, more like Polkadot, that we were looking at?
Yeah, so I think like the right way to say this is, logically it's the same. The separation is actually in who designs the protocol. So for execution sharding, the way execution is defined on those shards is defined by the base layer protocol. So it will be us protocol designers who would like write the whole specification, get clients to write all the code, everything. And for rollups, instead, it's independent teams who can write them as smart contracts. So instead of the logic for execution being defined inside the base layer, it's on top of the base layer inside smart contracts that it's defined.
That makes sense. And so at the same time, you've got these teams that are also deciding what's the new way that you can kind of transition state. And so you've got this difference in authorship and maybe a bit more opinion about the way that these computers are running.
Yeah, so I mean, there are some advantages, which are basically, it allows a lot more experimentation with different models. So rollups can both try out new VMs, which is basically, I mean, back when Ethereum was first created, it created its own VM, which was the natural thing at the time, because nothing like this had been done before. There was no VM available that would have just like fit into what Ethereum needed. But obviously, like, it came with a lot of problems later on when people realized, oh, like, when you just design a VM from scratch, you probably don't get everything right the first time. And so we're living with all these problems. And the cool thing about rollups is that they can now take on the baton, and we, instead of having one team that designs execution on all the shards and maybe makes these mistakes again, we get 10 or maybe even 100 teams designing different VMs. And yeah, we'll see which one is actually the best and which one, or maybe it depends on the use cases as well.
Okay, so we've now got these layer 2 computer things, and they seem to be dealing with kind of a lot of the overhead of what we were saying was sort of execution scaling, sort of checking that the stuff is internally consistent. So then, I guess when you arrive at the Ethereum Foundation, pretty quickly within 12 months, it becomes apparent that the sort of the main role that you have to tackle is the data scaling piece. And so I wonder whether we could go into what is actually a question you gave to me and thought would be a good place to start for those who are not familiar with this area. What is the difference between data storage and data availability? What does data availability mean? It's a very mystical term, and for those who are not familiar with blockchains, it might not be obvious what that is. So what is sort of data storage versus data availability, and what problem is it that you have been tackling under a sort of an eponym that's now called Danksharding?
Yeah, so data availability is, I think, like, the term is kind of unfortunate, but it's stuck now. I think better terms that I could think of would be either data publishing or proof of non-withholding of data. So what data availability means is that we have some data that the blockchain knows about, but not necessarily in the actual data form, like rather a commitment. And it knows that the data could not have been withheld by any party. And any party here includes a majority of the consensus nodes. So even if all the validators on Ethereum colluded and said, we want to create a chain with this data, but we don't want to publish the data, they would not be able to do this, because the normal Ethereum nodes that people run in order to access the chain would be checking that the data is actually available. So it's this property of non-withholding of data that we want. And what it doesn't mean is that the data is like, let's say it like this. What the Ethereum blockchain does not in itself guarantee is that this data is going to be stored or anything. We just say, for a number of weeks, this data is available and anyone who needs it can download it. And I think like my best analogy for it is, it's kind of a public notice board. Like it's like, there's someone requesting, I don't know, like a planning permission or something, and you want to make sure that anyone who wants to see it has a chance to see it. So you put it on a public notice board for a certain amount of time, and anyone has a chance to see it, and that's it. That's all you need to do, because like, as long as one party, and that's also like, I guess like back why I don't care so much about storage, because storage is actually easy. Like, in order to store the data, you just need at least one party.
Well, it looks like yours is gone. Well, you're more important than I am. Do you want to?
I think my mic, hello? Yes, okay, it's back. So storage is actually easy because once you have the data published, any single party, anyone in the world just needs to store it and it's there. So it's a much easier property to achieve than this data availability or data publishing, which needs to hold in the face of like a colluding supermajority of validators, for example.
That makes sense. I guess, obvious first question, particularly those who haven't been looking at this for a while, the layer 2 seem to be taking on a lot of jobs, and they're taking on this sort of this scale. They have this sort of temporary ability to determine what the order of the transactions is. They have the ability to process those transactions, put back a proof on chain. Why is it so important that the layer 1 deals with the administration of the data guarantee? What is it important that that still remains your job, not a layer 2's job? What's the difference between those two potential models?
Right.
Are we gone again?
Yeah. So the reason is that an L2 cannot get the same data availability guarantees as the L1. So it's actually, if you know a little bit about blockchain, it's relatively easy to prove that you cannot derive data availability guarantees by any other means than the L1 providing it in some way. So it has, like, for example, you cannot implement data availability sampling, which is the way we scale data availability, as a smart contract. It's just not possible. You need to have it as a base layer guarantee. So that's why we have to implement it.
This works now, great. Okay, so is this also to do with kind of the temporary guarantee versus long run guarantee things? So you're okay to trust layer 2s with some sort of temporary trust assumptions? Is that a good intuition for what's going on? But the long-term stuff, the archival stuff, the sort of the long-run belief in what the blockchain says is ultimately a layer 1 guarantee. Is that sort of a good way to think about it?
No, I wouldn't express it like that. I would say it's Okay, so the reason why a smart contract cannot do this is because data will be a property of the fork choice. Like the chain has to fork in a way that guarantees that whatever fork it's on, it's always the data for that is available. And a smart contract cannot do that. It cannot select a different chain than everyone else is on.
Got it. Okay, so we now have this concept, what we call a data availability scheme. So this is kind of the way that you are looking after the availability of that data, allowing people to sort of prove that it's there. First of all, what do we mean by a 1D data availability scheme? Can you give us a really intuitive introduction to erasure codes and like sort of how are you thinking about the trade-offs of these schemes? And obviously we're walking towards giving hopefully the audience some idea of dank sharding, but what's the most basic instance of this scheme that you could describe to the audience?
Yeah, so, okay, in very short, what data availability sampling is you take your data and you encode it in such a way that some subset of that encoding is always enough to get the whole data. And it's simple, like if you know computer science or so, you might have heard of Reed-Solomon codes. That's one easy way of doing this. You extend the data to say twice the length, and then any 50% of that will be enough to reconstruct it. And what that means is that when you get a certain number of random samples, you can very easily get a very high probability that 50% of the data is available. Because if less than 50% is available, each sample has a 50% chance of failing. So that very quickly, it scales exponentially. And so that's the basic idea. And you can construct a data scheme based on that. So that's perfectly possible. The one problem with that, if you just apply this idea directly, is that what happens if not all the data is available? What happens if, yes, there's say 99% of the data available, but some of the samples are missing? We want to get to a state where all of the data is available. Okay, so if we use this scheme, then someone has to download the whole data, because the only way to reconstruct the Reed-Solomon code is to have, well, not necessarily all the data, but at least 50%, which is already a lot. We want to create very large blocks. We're trying to scale blockchains so that billions of people can use them. So there's going to be a lot of data. And so that's why we had to think a bit more and apply a bit more maths and come up with a way where you can get the data back even without anyone having to get 50% of the data, with people using much, much less of this data. And that's where the 2D schemes come into play. That's why we have two-dimensional schemes, because then, for example, you can get things like you can reconstruct rows and columns of the scheme individually.
And maybe before we get onto the 2D bit, what's the difference between these sort of 1D erasure codes and just cut up the network into sort of partition sections and you get 20% of the data and you get 20%? What's the difference in the level of guarantee that these sort of Reed-Solomon codes are giving you?
So if you don't encode the data, if you just take the data itself and say we just shard that data and everyone gets random samples of that data, you have the problem that any single part of the data is missing, is only detected by a small minority of the network. Most people will not notice it. And so a malicious actor could hide some of the data. Some very small amount maybe, but they could. And unfortunately for at least for the blockchains that we're creating now, which like have a lot of like financial application and so on, that's just a no, like it doesn't work, because you could create inside that tiny missing piece of data the transaction that creates 1 billion ether, and clearly that will be broken. We can't allow that. So unfortunately, we have to have this very strict notion of data availability.
So with this new data availability tool, I think a lot of people have heard of this encoded as EIP 4844. When can we start to sort of see this in action on Ethereum? What's the best guess for the time to delivery?
I hope this year.
And when it comes this year, what does that mean for roll-ups and their kind of sort of economic feasibility and their performance?
Yeah, so we are hoping that rollups will become a lot cheaper to use. So right now, the rollups have to compete with normal Ethereum transactions for their data, which turns out to be quite expensive. Once we have EIP 4844, they have their own little separate data market. Yeah, I mean, as far as I know, there's already a lot of teams are building on this. I'm very excited. It's gonna be great, because I think like it will be the first time that that we see actually like some scaling on blockchains in action, where people will be able to use something, yeah, do the things that we've promised 10 years ago on blockchains.
Very exciting. That's great to hear it's coming this year. Maybe looking a bit out to the future, you've obviously got your work cut out for a few years at least. 64 times, whatever it might be, kind of redundancy, not quite, but are you going to have to do this exercise again at some point? Sort of when does Ethereum, is there any point at which Ethereum stops having to keep on optimizing its data availability sort of schemes, accommodate more roll-ups, more transaction volume? When does that kind of cycle stop for Ethereum? I mean, I presume it goes on beyond just 4844.
Yeah, so we are hoping, I mean, okay, so right now 4844 is clearly this intermediate step that brings in all the cryptography for sharding, but it doesn't scale yet. So it's like it still puts all the data on chain. And we hope that within the next 1 or 2 years, we can make a networking change that introduces data availability sampling, which will allow us to scale it. And we can then, I think, gradually turn up the amount of data we can put on chain.
Final couple of questions. Okay, so probably there's a good few people in this room, probably computer science, physics, mathematician graduates, so maybe some people from engineering and other fields. You're quite unusual that you came to this afresh. You kind of, even actually when you arrived at Ethereum Foundation, I think you were saying earlier, it was basically a standing start and you had to learn this stuff on the hoof. For those who kind of want to get a sort of head of speed now, where would you suggest, which sort of resources do you think, cryptographers are famous for encoding heavily their intellectual output, and in certain cases, and it's quite hard to read, at least for the new entrant. Where are the best places to start so that people can start to sort of intuit the core primitives of cryptography if they're about to graduate or just wanting to get into it now post-graduation?
Yeah, I mean, I guess the cool thing about what we've done in the last few years is that there has been this very blockchain-centric ZK space that has developed, and I think like there are a lot of good podcasts and talks and everything out there that try to explain things in relatively understandable terms, and I think there are a lot of online resources on that. So I recommend starting with that. With cryptography papers, I mean, I think like it varies hugely, but there are very accessible ones, and you can try reading those. There are unfortunately also more difficult ones that are not as accessible if you haven't read it before.
So I guess ETH Research, I know you've got a great KZG primer, and I expect other primers online as well. So I guess that's a good place to point people to. Final quick question. let's sort of think about the crypto anthropologists of 20 years' time, and they're going deep sea diving at layer 1, and they're looking at the Ethereum virtual machine. What is that machine doing? As in, what is it processing? Is it basically checking proofs and administrating state executions of layer 2s? Is there much other activity going on there? I guess hard to look ahead, so horrible question to ask you, but what do you think?
So my best guess is that it's going to be, yes, there will be a lot of proof checking, but I don't believe all activity will ever migrate away from L1. So I think my guess would be if Ethereum still exists in 20 years, we will also still see activity on L1 in 20 years. People will still be writing smart contracts on it, and it will be pretty expensive. We will also scale L1 at some point. We have several works in the project, like up in the process, like for example, statelessness will probably allow us to scale it by a factor of 10 or so, I would reckon, which is also quite a big factor. And then I think in 20 years, it is very likely that the base layer itself will be a kind of ZK EVM. So it will probably scale quite a bit further than that over that time.
Thank you. Well, Dankrad, thanks to your efficient answers. We've come in on time. Thanks very much indeed for speaking to the crowd. And yeah, I'm sure lots of people want to speak to you after the event.
Yep. Thank you for having me.